Hey everyone, and welcome back to Prefusion. I'm Anish, and today we will be solving the control system questions from the doubly branch of Gate 2024. So, before starting, I want to say that the question, what I felt was the question level was moderate, paper was lengthy, but that was made lengthy intentionally. You had to skip those questions basically. You had to skip those in the first round. You had to solve the easy and the fast solving questions. Then in the second round, you solve the doable questions, but they are lengthy. So that's how you proceed. So that should be your strategy. So if you are stuck in something, or if you're stuck in a strategy or something, if you're depressed, you can text me in Telegram, right? I can help you in some way, but I won't have too much time. Just I can reply once or twice. So yeah, if you are depressed or something, you can text me, because many people told that the paper was very tough. Personally, I didn't feel it was that tough. It was definitely moderate. The paper was lengthy, definitely, I do agree with that, but it was not like the previous year. It was not like the 2023. Okay, that I can definitely say. Okay, so let's start with the solution of control system. So this is a simple question. You have been given a block diagram, and you have to find the transfer function. Basically, you have to find the ratio C upon R of S. Now many teachers, what they tell you is that you remember this shortcut, okay, then you remember this shortcut, that shortcut. No need to do that. Simply you solve with basics. Okay, because if you shortcuts does help in time. Okay, we also use shortcuts, but not always. Okay, because sometimes mistakes can happen when you are using shortcuts. Then we are most vulnerable to mistakes, so be careful about that. So here what we can do, this is c, right? This is c. I will just write c. It is understood that it is a function of s. So here c is coming. So at this node, what is the value at this node? R is incoming here, R minus c. So this will be R minus c. Okay, now this is R minus c. Now again I have a negative sign over here, and what is coming over here? C is again coming over here. So c minus this component, this term, which is R minus c. So here what do I have? C minus R minus c. Okay, this is the component I have. Again I'm multiplying with this gain block g of s. Okay, so if I multiply with this gain block, I should again get back c. That is the main thing. That is how I solve this simply. Okay, so yeah, now this will be, what will be this? This will be c minus r plus c. So this will be 2c minus r into g equals to c itself, because the multiplication of this I'm getting back g again. Okay, so yeah, let me just further simplify this. So this will be 2cg. I'll take c over here, and this will be rg. Okay, and yeah, rg will go over that side, and minus, yeah. So now what will happen? This will be simply c of s. Now we'll write upon r of s equals to g upon 2g minus 1. I'm just taking common c over here. This will be 2g minus 1, and I'm just taking common g, like this is r only. So g upon 2g minus 1. In the options, 2g minus 1 wasn't there. What I recall correctly is that it was we have to take a minus common. This will be g minus g upon 1 minus 2g. So this was in the options, if I recall it correctly. Okay, so this will be the answer for this question. Just, this is a very simple question. Don't do any mistake in the simple questions. This is the these are the questions in which you will gain marks. Okay, so yeah, minus g upon 1 minus 2g. Okay, now what is this question? This, you have been given a OLTF, k into s square minus 2s plus 2, s square plus 2s plus 5. K is varying from 0 to infinity. That means basically we have to find the angle of departure. That means this is a normal root locus problem. K is positive always, and your theta will be 0 to 360. This angle of departure will be between 0 to 360. Now they have asked you to find the angle of departure. So how will you find it? So what you can do, either you can use the formula, or you can simply use that, how the angle of departure came, use that also. Okay, I will try to show you both of the ways. So here, what was the angle of departure formula? So if you recall correctly, my theta d was equals to, now first, before, why is it departure, why is it arrival? Let's see. So if I just draw the pole 0 diagram of this OLTF. So where are my poles? So you have to identify them quickly now. So my real part of my pole is lying on -1 because minus b upon 2a. So that is the real part. And whether, like, what is this? This is imaginary or real, we'll see. So just let me quickly compute the poles. So the poles will be minus b plus minus b square minus 4ac 20 divided by 2. So this is 4. So this is -1 plus minus g2. Okay. Now what is sz? Sz is simply minus b is plus 2. Now this is on the right hand side. Plus 2 plus minus b square. B square this time is again 4 only, and minus 8 upon 2a. So this is 1 plus minus j. Okay, these are my zeros and these are my poles. So let me quickly draw the pole zero diagram. From here we will understand many things. Sigma j omega. Okay, so where does my poles lie? My two of the poles, these poles lie here. Okay, this is -1 point and this is j2 minus j2, and two of the zeros lie here, around here. Okay, plus j1 or minus j1. Okay, so now what you have to find? You have to find the angle of departure minus from at -1 plus j2. So -1 plus j2 is here. Okay, so you have to find the angle of departure. So obviously what we do is we find all of the angle contributed due to other poles and zeros. That is what we find, right? So angle contributed this due to this pole is what in this pole. So this is what I'm looking above in the anti-clockwise direction. Looking up in the anti-clockwise direction, I'm moving 90 degrees. This is exactly in the top of me, in front of my head, above my head. So this will be plus 90. Okay, in the anti-clockwise direction. That's why it is plus. So like we'll find the individual angle contribution due to the poles and the zeros. So first I will write the what is the departure angle formula. Departure angle formula is theta d equals to even either at plus minus 180, it doesn't matter. So plus 180. Now what will come? Theta z will come minus theta p, summation of theta z minus summation of theta c. Minus summation of theta p. So this is my angle of departure formula. Okay, if you recall correctly, I'm not explaining any concept here. So now what is the angle contributed due to this pole? It is 90 degrees. So theta p will be 90. Is there any other pole? No, there isn't any other pole. So simply it is plus 90. Okay, now what is the angle contributed due to this zeros? Now very careful. So here I have to move. This is -1, this is -1, this is +1, right? This is +1. So here I have to move 2 steps backward. Okay, 2 steps backward and 1 steps upward. Okay, 1 step in the positive y direction and 2 steps in the negative x direction. So negative x and positive y, which quadrant is it? It is in the second quadrant. So if it is in the second quadrant, that means my angle will be what? 180 minus theta again. Okay, so like all these things I have explained. The basics of angle I've explained many times. Okay, so theta z due to like angle contribution due to this zero will be what? 180 minus theta, which is tan inverse. What is the distance I'm moving in the y direction? This is plus j. This is plus j. Let me write this. This is plus j and this is minus j. This is plus j. So I'm moving in one unit, as this is 2j. Okay, this is 2j. So yeah, moving in y direction in 1 unit, and in x direction, how many units I'm moving? 1 unit and another unit. So this is 2 units I'm moving in the x direction. Now what is the angle contribution due to the zero on this pole? Now in the y direction I'm moving in the positive again, in the upwards again. I'm moving in the this is -1. I have to move 3 units. 3 units I have to move. Okay, and in backward direction I have to move 2 units. Hence again my x coordinate is negative. That's why I will write again 180 minus tan inverse theta, because it is lying in the second quadrant. So plus 180 minus tan inverse. This is moving in the y direction in 3 and x direction same again 2. Okay, so let's say let's basically calculate this theta z and theta p is already calculated. So one thing we observe is this is like 180 plus 180 only, so this is 360. We can ignore this. 360 equals to 0 in terms of angle condition because we are moving one circle. So what is minus tan inverse 1 by 2 and minus tan inverse 3 by 2? So let me just quickly calculate them. 0.5 tan inverse minus 26.56 degree and 1.5 tan inverse minus 56.3 equals to minus 26. Okay, just do it. Yeah, this is plus almost 80 minus 82.87. Okay, and we had a plus 90 over here. So what will this? This will be simply 180 minus 82.87 minus 90. So this will be around I 7.13, which I recall. 82.87 minus 90 plus 180, 7.19, or very near about that. Okay, so yeah, this will be the theta departure. Now what other concept we could have used? So if, like, this is where the formula comes from, like basically this is from where the formula comes from, is that we know that this point is lying on my root locus. This point is lying on my root locus. If this point is lying on my root locus, then it has to satisfy my angle and magnitude condition. So if I use the angle condition, from there you will understand that if I if I put this in the OLTA, basically what is my g of s? My g of s is what? My g of s is k into s square minus 2s, s square minus 2s plus 2 divided by s square plus 2s plus 5, okay, equals to k in now what is this, like this is my OLT, right? Now if I put that value, if I put s equals to minus 1 plus j2, that should satisfy my angle condition because that is lying on the root locus. So that is what we'll do. Now what we can't do is, we'll assume that, like that is how I proved in my class, basically, that we take a test point which is very near this, but not exactly equal to this. If I put exactly equal to this, then what will happen? My OLT will blast, basically, because my denominator will go to 0. That's why. Okay, so like I can further simplify this like this, that this is s, like with the 2 zeros and 2 poles, so it is minus plus j and s minus 1 minus j, like zeros were at minus 1 and like plus j and minus 1 minus j, and like just factorizing them, this is s minus 1 plus 2j and s minus 1 minus 2j. Now if I put s equals to plus 1, s equals to, sorry, this will not be s minus 1, this will be s plus 1, sorry. Okay, so if I put s equals to minus 1 plus 2j, then this will blow up. Okay, that's why we take a test point which is very near to this, and we find the angle contribution due to that test point. Okay, so what we do, simply we put s equals to minus 1 plus 2j for all of this, like it is almost equals to minus 1 plus 2j, but just very near it. Okay, so like this I have taught in my full concept, so I won't explain it very further here. From here we derive the formula for that angle of departure, basically. So I can write s equals to minus 1 plus j2. Okay, so s equals to minus 1 plus j2, so this will be minus 1 plus j2 minus 1 plus j minus 1 plus j2 minus 1 minus j, this will be minus 1 plus j2 plus 1 plus 2j, and this, right, this I will assume some function, okay, some function, okay, which is very near to this. There is some error function which is very near to this, okay. I'm assuming this is very near to this. That this is how we prove. Now this is equals to what? This is equals to, this should be equals to -1, right? This is lying in the root locus. Again, I equate this with the angle condition. So if I equate this with the angle condition, so let me write this. So what will this become? This will become -2 plus j3, okay, -2 plus j3, then this will become -2 plus j, okay. Just let me write this over here. This will become 0 and this will become 4j, and this I am writing as epsilon, okay. This is very near to that point but not exactly equal to that. That is how we test it basically. That is the basic concept of angle of departure. So this is equals to -1. Now we apply the angle condition. So if we apply the angle condition, this will be equals to -180, okay, and this will be equals to like this is lying in which quadrant? Again the second quadrant. So this will be again -180 and this will be that again. So now, and what will the angle? This will be, I will assume this as theta d. This will be as theta d, and all this will contribute how much? -90 degree, okay. And if you equate that, you will get your same answer. I'm just not wasting any time, okay. So now the next question, it's like a good moderate question, because like if many of people like don't know the formula, and you can solve it basic also, but it will take time. So all of these questions were lengthy, that I definitely agree. All of these questions were lengthy. So here you have been given a stable closed loop system. It has told that the system is stable. It has already told that the system is stable, okay. This is the first important point. The asymptotic Bode magnitude plot has a constant slope of -20 dB per decade at least till 100 radian per second. So before 100 radian per second, the slope is always -20 dB per decade. So it is starting from -20 dB per decade. What does that mean? That means I have a pole at s equals to 0, okay, single pole at the origin, as our slope is -20, okay, with gain crossover frequency being 10 radian per second. So if I just draw the transfer function, omega magnitude of g of omega, so it is basically something like this, okay. And gain crossover frequency, what does gain crossover frequency means? It means the frequency at which the gain of my OLT is 1, or in dBs it is 0. So here it is 10 radian per second. So this is 10, and up until 100 it is -20. So I don't care about after that. Why, we'll understand in a bit. Now the asymptotic Bode phase plot remains constant at -90 till 10 radian per second. So till 10 radian per second, my asymptotic Bode phase plot is constant. It is -90. From 0 it is from 0 radian per second up until 10 it is -90. So and at 100 obviously there is some change. I don't know if there is some change or not. Why they told us 10? Because it is very important to note here is that like here there may be pole and 0, so may change, okay. Now if there is a pole and 0, the effect in the phase plot, what will happen? The effect starts 10 times before this and 10 times effect starts from 10 times before this and ends 10 times after this, okay. So the effect of this pole or 0 will start from here. That's why they only told that up until 10 I can tell you that it is -90 degrees, but after that it may change, because the effect due to this pole or 0 or whatever, like if there is a pole or 0, the effect will start from here. That's why. So that's why they told like that. So this is -90 degree, okay. Now at least till 10 radian per second. Now okay, that's fine. Now they are asking us to find the steady state error of the closed loop system for unit ramp input. Now it was an NAT question. Okay. Unit ramp input, you have to find the steady state error. Now you see like this is a type 1 system. Yeah, you can use that formula you wish. Now you might ask, sir, but in the easy question you solve it so lengthy, like you find the stability and all those things. Here you will not find the stability. Why? No, because firstly this is the entity type question, so straight error cannot be infinity, cannot be oscillatory. You have to write single value here, single input. That's why. So whenever entity type question comes up, like all these things also you have to analyze. You don't have to analyze stability for this, because straight error, like if it's oscillatory, then we can't find for it. Okay, that will be empty. So that's why we won't check stability here. But there, why we checked? Because in the options, if all the 4 options were constant, no issues, we won't check for stability. If even one of the option is none of the above, or it is telling like it is oscillatory or steady state error does not exist, then we have to dig deeper. We have to check the question. That is the main thing, right? So that is how you decode the options as well. Okay, not only the question, the options is also important. Okay, so now basically what you do is you can either use the formula. Okay, what is the formula? So first I will show the formula. So like for a type 1 system, what is the transfer function? Like how I can write the transfer function? I can write like before coming this pole, up until this pole, I can write my transfer function like this: k upon s square. Okay, k upon s square. There may be some poles. Okay, I will write this in time constant format. Like we write the Bode plot in time constant format only. So there may be poles s tau 1 then s tau dash 1 okay. But what will happen is that at DC, basically not at DC, at here, at this point, this will be my k value, because for type 1 system or for like when initially my slope is some type system. Okay, this is not s square, this is as simple as. So if we call the formula very well, I will show you without the formula as well. So what is without the formula? It is like this is equals to omega gc. Basically this is equals to k equals to omega gc for a type 1 system. Okay, so k is equals to 10 over here. Now you might say, sir, I don't remember the formula. How to solve. So how to find the value of k? So what you can do is you take a point here. Okay, omega equals to 1, and at omega equals to 1, what is my magnitude? At omega equals to 1, what is my magnitude? So at omega equals to 1, magnitude is not at omega equals to 1, I meant like omega equals to 0.1. That is why that approximation comes up. So omega equals to 0.1. okay, omega equals to 0.1. what I can approximate is that like the magnitude contributed due to all of this will be very low. Okay, now what is the magnitude formula? It is k upon omega into omega tau 1 square plus 1 under root omega tau 2 square under root. Okay, now what I am assuming is all the poles lie very further away. So if my omega is very low, okay, then this omega square term will be even lower. Okay, that's why all of this this one will be ignored, only the 1 square will be remain. So only 1 times 1 times 1, and here in the denominator also 1 times 1 times 1. So only 1 term is remaining. So our magnitude will be this only, k upon omega. Okay, so what is omega? It is 0.1. So this is 10k. At omega is to 0.1, my magnitude is 10k. Okay, in dBs it is 20 log 10k. Now we will simply use the slope formula. So what is slope? So we know slope equals to, let's mark this point as a and let's mark this point as b. Now slope AB is what? Slope between a to b is constant, which is minus 20 dB per decade. Okay, that is what we know, which is equals to yb minus ya by log of base 10 omega b by omega a. Okay, so here what I can write? I can write that what is yb? Yb is this point, it is 0 dBs. 0. What is ya? Ya is this magnitude, which is 20 log 10k. What is omega b? Omega b is 10, omega gc, which is 10 in our case. and what is omega A? It is 0.1. Okay, now this is also log 10 base 10. Now from here, if you equate, you will get your value. So my log 10 base 10 equals to log of 100 base 10 100. Hence 10k equals to 100. Hence k equals to 10. Like if you can't recall, okay, if you want to solve from basics, you can solve from basics also. Okay, so but you have to understand the concept possible. So like this will take you like 30 seconds more. I'm explaining you, that's why it is taking so much time. Okay, so now k is 1. So now you can find the steady state error. What is the steady state error formula? Again, you can go through the basics. You watch my previous video where I've derived the formula for steady state error. Else, like we know the system is stable, we can use that formula also. Velocity error coefficient. So my kv, what will my velocity error coefficient? Kv will be, as we have been asked for a ramp input, limit s tends to 0, s g of s. Here in this case, like all other terms will go away, only k will remain. Okay, only k will remain because like it is k upon s over here, k upon s over here. We'll multiply s with this, so this will get cancelled and all of this term will go to 0 and k will remain. Okay, and k is equals to 10. K is equals to 10. So what is my steady state error? Steady state error is 1 by kv, which is 1 by 10, which is 0.1. Okay, you can use the formula or you can use the basics also. I have solved this in the previous in the EC shift steady error question. You can watch that video. I am not repeating again. Next question is again simple only. Basically, you have been given an underdamped system. Okay, standard underdamped system, and you have been given the parameters omega n and theta. From theta we can find zeta. Okay, theta is basically the angle from the negative real axis. Okay, to remember the definition of theta. So two systems are given and you have to comment on the settling times. So what was the formula for settling time? First of all, you have to understand that yes, this is the underdamped system. That's why the discussion of settling time comes up. Okay, so yeah, that way to check what type of damping is present. Without that, you don't proceed. Now, as this is an underdamped system, now you check what is the formula of settling time. As they haven't mentioned anything, you will use the 2% error band formula. So this is 4 upon zeta omega n. Now 2% error band formula is given. Now what you do is your zeta is changing and your zeta is equals to what? Zeta is equals to cos theta and omega n is also changing. So simply you just do the ratio t settling 1 upon t settling 2, which is equals to zeta. Now this will be inversely. So this is cos theta 2 into omega n2 upon cos theta 1 into omega n1. Okay, so like what is cos theta 2? Theta 2 is 70 cos 70.342 into omega n2. Omega n2 is 1 and 60 0.5 into omega n1. Omega n1 is 3. Okay, so you can check that obviously it is much higher. T settling 2 is much higher. Okay, so your T settling 2 will be greater than T settling 1. Hence my option, this B will be correct. Okay, so I don't know like what were the order of options. So this option is T settling 2 is greater than T settling 1. So I don't know the order of the options, you just check like, but answer will be T settling 2 will be greater than T settling 1. Now we have this last question. This is also a very good question basically. So phase margin of the given system is given, which is 50 degrees. Okay, now you have to find the value of Ki. Also you have been given the frequency response of G of S, basically the angle and the magnitudes. Now like how to solve this? So you know the phase margin. What is the definition of phase margin? Phase margin is basically 180 degrees plus the amount of phase lag. So plus the amount of phase lag present to this whole system. Now like from this OLTF, this is the combined OLTF, modified OLTF. Okay, so what angle is this one contributing? This is always contributing minus 90 degrees. Okay, like we have a pole at the origin. So this is always contributing minus 90 degrees. So that is fixed. And I don't know the pole of this. I don't know the angle of this. So I will write this in unknown terms, g of s. Now, at what frequency? At gain crossover frequency. So if you remember, we find the phase margin at the gain crossover frequency. So this is omega equals to omega gc. Okay. So this is one case. Now they have told us what is the phase margin. They have told us the phase margin is 50 degrees. So we write 50 degrees here. This is 180 plus this is also minus 90 is also present over here. So this will become 90 plus g of s at omega equals to omega gc. Now this is always minus 90, so it doesn't matter. So my angle at gain crossover frequency is minus 40 degrees. Now my angle is minus 40. In which location my angle is minus 40? Here, right? Omega equals to 0.5. So omega equals to 0.5 is my gain crossover frequency. Okay, like this is how you decode these questions basically. Like you have to write, you have to start writing. Once you start writing, then your next step will automatically come up as you have practiced many questions in the test series. So this is omega gc. Okay, now so this is omega gc. Now what next you do? Now what you have to find? You have to find the value of ki. So what happens at omega gc? At omega gc, my gain is 1. So magnitude of basically this omega gc is the gain crossover frequency of this whole system, not just this system. Remember this. That's why the magnitude here isn't like 0 dBs, because 0 dBs is 1. That's why it is not 0 dBs, because the whole thing, the magnitude of this whole thing is combined thing is 1. Okay, gain crossover frequency. So magnitude of ki upon s into g of s, or I should write this like s equals to j omega gc equals to 1. Okay, so this will be ki by omega gc into magnitude of g of j omega at omega gc. Okay, so this I can write omega gc. Now what we can do is we can take log on both sides. So if I take log on both sides, this will be 20 log ki upon omega gc. What is omega gc? Omega gc is 0.5. So this is a very good question, but basically you have to find information from here and there. So this is doable. Okay, now this is 0.5. This is plus, in dB is 20 log of this. Now we already know the magnitude at omega gc of this g of s. This is what? Minus 7. They have given us minus 7. So this will be minus 7 dBs, and this is 0. 20 log base 10 1 is 0. Now this will be ki equals to 0.5 into 10 raised to power 7 by 20. Okay, so let me just calculate this. Almost 1.12. Okay, so ki will be 1.12. This will be answer. So I solved all of the questions from control system. So if you like the solutions, also I try to provide concept as well. I just didn't simply solve it. Okay, so that you can take something from this video. So if you like the solutions and if you like the concept, then don't forget to hit the like button, and I will see you in the next video.